Welcome back to the deep dive. We spend a massive amount of time analyzing the electric vehicle market here.
Oh yeah, constantly.
Right. We look at battery chemistry, we debate charging infrastructure, we argue about self-driving software. But today, we are looking under the hood, literally, at the actual industrial reality of how these machines come into existence.
Which is funny because we usually completely ignore the manufacturing process. We just assume that because an EV looks like a traditional car on the outside, the factory floor is basically the same.
Exactly. Making a car is making a car.
But it's not. The shift from internal combustion engines to EV platforms is a totally different beast. It is essentially a total dismantling of a century of machining knowledge.
And that is exactly our mission for today's deep dive. We're jumping into a fascinating source text from ISCAR titled Precision Tooling Systems for Next Generation EV Production.
And calling it just a tooling brochure really doesn't do it justice.
No, I mean, it reads almost like a manifesto on the changing physics of the factory floor. The core thesis here is that we have to stop thinking of cutting tools as isolated, consumable components. To make EVs, you need a shift toward integrated systems.
That distinction is so vital for you to understand if you really want to grasp the EV revolution. In the ICE era, the internal combustion era, you had these massive cast iron engine blocks. They were heavy, they were forgiving, you could just power through them with standard tools.
But now, based on the dossier, the focus has completely shifted away from engine components toward massive aluminum structures, battery housings, and incredibly high-precision motor parts.
Right, and hardened steel shafts that have to handle instant torque. The tolerances are bordering on aerospace standards now. ISCAR's position is that if a manufacturer doesn't use a broad portfolio of specialized application-driven tool systems, they aren't just going to be slow, they're going to produce massive amounts of scrap.
Let's start with the most obvious shift, which is the material itself. We've moved from a world dominated by heavy iron to a world dominated by aluminum alloys.
Specifically for battery housings, trays, and structural frames.
Right. And the source emphasizes this is all about lightweighting to offset the massive weight of the battery packs. But I was genuinely surprised by the specific machining challenges this introduces. It's not just that aluminum is softer, it's actually
chemically problematic.
Yeah,
it's the ductility that kills your efficiency.
Right, because when you are machining aluminum at the crazy speeds required for high-volume auto production, the heat generation is intense.
It is. Aluminum doesn't just chip away cleanly the way cast iron does. When it gets hot, it gets gummy. It reaches this plastic state.
And the dossier calls this the built-up edge phenomenon.
Built-up edge, exactly. It's basically a form of adhesion. The hot aluminum literally pressure welds itself to the cutting tool.
So you aren't even cutting with the sharp carbide edge anymore.
No, you are trying to plow through precision material with a blunt lump of melted aluminum stuck to your cutter.
Which I have to imagine is just catastrophic for the surface finish.
It destroys the finish. But even worse, it changes the geometry of the cut itself. It increases your cutting forces. Think about a battery tray. It's this huge, intricate component with incredibly thin walls to save weight. If your cutting force increases, you get vibration.
Chatter.
Right, chatter. And if you get chatter on a thin wall, you violate the dimensional tolerances and you scrap the entire part.
So to fix this, ISCAR introduces their Hili-Alu milling cutters. And the specific feature that stood out to me wasn't just that they are sharper, but they have polished rake faces.
Yes.
Now, I usually associate polishing with aesthetics, like making something look nice, but here it sounds like a strict functional requirement.
Purely functional. It's all about the science of friction and wear. The rake face is the surface the metal chip slides against as it's sliced off. By polishing that to a near-mirror finish, they drastically reduce the coefficient of friction.
Oh, I see. So the aluminum has nothing to grab onto.
Exactly. They eliminate the microscopic valleys where the hot aluminum can stick. If the chip slides off instantly, it carries the heat away with it. The tool stays cool, the edge stays clean, and you prevent that built-up edge.
So it's essentially heat management through geometry. That is fascinating.
And that is what allows manufacturers to run these Hili-Alu tools at the really aggressive feed rates they need without warping those thin aluminum walls.
Now, there's another layer to this aluminum challenge that the text emphasizes, and that's flexibility. The EV industry is moving so fast, battery designs are changing every single model year.
It's a logistical nightmare for Tier 1 suppliers.
Right, and the source brings in the multi-master aluminum milling heads in this exact context. It seems like a supply chain solution as much as an engineering one.
It totally is. Think about a supplier making battery trays for 3 different car brands. One might use a cylindrical cell pack, another uses prismatic cells. If that factory has to stock thousands of solid, specialized carbide tools for every possible geometry, their inventory costs just explode.
Plus the downtime. The setup time to change those solid tools out constantly would be terrible.
That's where the multi-master modular system comes in. It uses exchangeable heads on a common tool platform.
Yeah.
You keep the steel shank inside the machine spindle, and when the cutting edges wear out, or if you need to switch profiles for a totally different battery tray, you just swap the carbide head.
But doesn't that introduce a weak point? I've always understood that solid tools are inherently more rigid. If you put a screw thread right in the middle of a milling tool, aren't you risking vibration?
That is the historic objection, yeah.
Yeah.
But the engineering in the thread interface is the secret sauce here. ISCAR uses a tapered interconnection that locks the head in with rigidity that is basically comparable to a solid tool.
And the text points out the huge advantage is repeatability.
High repeatability.
Yeah.
Because the interface is so precise, you don't have to remeasure the tool length every time you change the head. That saves minutes per setup. And in a factory running 24/7, those minutes add up to millions of dollars.
Okay, let's pivot from the frame to the actual heart of the EV. We've cut the lightweight chassis, now we need to power it. The report moves into electric motor precision. We're talking housings, stators, rotors, and the keyword here seems to shift from speed to silence.
It's all about NVH. Noise, vibration, and harshness.
Right, because in a gas car, you have thousands of explosions happening every minute. That masks a lot of mechanical noise.
But an EV powertrain is virtually silent. If there is even a microscopic geometrical imperfection in the motor housing, you get a whine.
And that whine isn't just annoying for the driver, it means the car is inefficient, right?
It's pure energy loss. To maximize efficiency, the air gap between the stator and the rotor in a modern EV motor is incredibly tight. The source talks about using precision boring systems to finish the bearing seats.
And just to clarify for everyone listening, boring in this context doesn't mean making a hole from scratch. It means refining an existing hole.
Correct. The hole is already cast or drilled. Boring is the final operation to ensure it is perfectly round and perfectly straight. And the dossier mentions these boring systems offer micron-level adjustability.
Micron level, that's extreme precision.
It means the operator can adjust the diameter of the cutting tool in increments of 0.01 millimeters.
Because if that bearing seat is off by even 5 microns?
The rotor shaft won't spin perfectly true. And since EV motors operate at 15 or 20,000 RPM, that microscopic wobble becomes a massive vibration generator. It destroys the bearings and creates that high-pitched whine.
Which means the tooling literally dictates the acoustic experience of the car.
Speaking of the motor, there is another feature mentioned that sounds like an absolute nightmare to manufacture: the integrated cooling channels.
Oh yeah, drilling deep holes, that is one of the hardest things to do reliably.
Because EV motors generate a lot of heat, they have these deep, complex paths running right through the metal housing to pump coolant. And you are drilling deep with a really high length to diameter ratio. The actual cutting of the metal isn't the problem there. The problem is getting the metal chips out of the hole.
Right, because if the chips get packed up inside those deep flutes, the drill just snaps inside the part.
And then you've just ruined a nearly finished, highly expensive motor housing. So ISCAR highlights the DR twist and the Logic 3-cam modular drilling systems for this.
And their whole focus is chip evacuation geometry.
Exactly. They design the spiral grooves on the drill to act like an Archimedes screw, actively pumping the chips up and out of that deep hole so they don't jam.
And I noticed the Logic 3-cam also uses that exchangeable drill head concept we talked about earlier.
It does, which speeds up tool changes. But the really interesting part is the 3 in the name Logic 3-cam. Standard drills have 2 flutes. This one has 3.
Meaning 3 cutting edges instead of 2.
Right, which allows for higher feed rates, but more importantly, better self-centering capability. It stabilizes the drill deep inside that cut so the cooling channel doesn't wander off course and accidentally punch through the wall of the housing.
That makes total sense. Now, another thing that ties right back into efficiency is the use of combination tools in these compact motor components.
The multi-master combination tools, yeah, that is a huge efficiency hack.
It really is. The source explains that a single motor component might need a hole drilled, the edge chamfered to remove burrs, and a flat face milled around it. Usually that takes 3 separate tools.
3 tools, 3 tool changes. The machine stops, swaps tools, spins back up. That chip-to-chip time is just dead time.
But these combination tools are designed to do the drilling, the chamfering, and the milling in a single setup.
One plunge. You plunge the tool, and the custom geometry handles all 3 operations simultaneously. It improves repeatability because you aren't realigning different tools, and it drastically cuts down the cycle time.
It's brilliant. Okay, so we've covered the sticky aluminum and the high-precision motors, but I think a lot of people assume EVs are just soft metals and magnets. But the drivetrain, the transmission shafts, the gear components, those are still steel.
Oh, and they are using hardened steels that are much tougher than what we saw in legacy auto manufacturing.
That's the instant torque, right?
Exactly. An electric motor delivers 100% of its torque the second you touch the pedal. There is no buildup. That puts a violent shock load on the transmission gears and drive shafts. So to survive that, the steel has to be hardened to a much higher degree.
And the dossier points out that machining hardened steel is incredibly difficult. It's highly abrasive.
It eats standard tools alive. The heat is extreme, and if your tool isn't incredibly rigid, it will just deflect. So ISCAR brings in their heliturn and logic turning inserts here.
And the text highlights their optimized wear resistance and edge stability for these hard materials.
Right. They are specifically engineered to survive that abrasive environment. But the real challenge is what the source calls interrupted cuts.
I wanted to ask about that. Why is an interrupted cut so significant on a shaft?
Well, imagine turning a steel shaft that has splines or cross holes in it. As the part rotates against the tool, the cutting edge is hitting metal, then hitting empty air, then slamming back into metal.
Oh, so it's a hammering effect.
Thousands of impacts a minute.
Yeah.
A standard tool will literally shatter under that shock.
Yeah.
So the logic turn inserts use a reinforced edge geometry designed to absorb that constant impact without failing.
And just like with the motor, the surface finish on these steel shafts links right back to the noise issue. The text specifically mentions cut grip, parting, and grooving tools, and it ties them directly to meeting stringent noise, vibration, and durability targets.
Because if you cut a groove on a transmission shaft to hold a seal or a snap ring, and that groove has a poor surface finish or a slight wave to it, it will induce vibration into the entire drivetrain.
And in a silent EV, the transmission gear mesh is one of the only sources of noise left.
Exactly. So grooving isn't just about making a slot in the metal. It's about sculpting a precision feature that ultimately determines the acoustic signature of the vehicle.
I just love how the demand for silence dictates the microscopic geometry of a cutting insert.
It's all connected.
It really is. Now, there are a couple more tool families I want to touch on before we look at the bigger picture. We talked about the chassis being aluminum, but the car still needs incredible structural integrity to handle the weight of the batteries.
Right, the structural parts. That's where they deploy the neo-feed, high-feed milling cutters.
And the specific function of the neo-feed, according to the dossier, is achieving very high material removal rates on both aluminum and steel structural parts, but with reduced cutting forces.
Which is critical for those structural nodes.
Yeah.
You need to carve out a lot of material quickly without distorting the part. And for more general tasks across mixed materials, they highlight the Hellamil 390.
The dossier really positions the Hellamil 390 as a versatile workhorse for shoulder milling and general applications.
Every factory needs that reliable generalist alongside the hyper-specialized tools.
Definitely. All right, I want to step back from the cutting edge itself now and look at the intangible side of tooling that the report gets into. It focuses heavily on digital intelligence and Industry 4.0.
Yeah, because ISCAR isn't just selling you a piece of metal to cut another piece of metal. They're offering full engineering support.
The text mentions the Logic Quick tooling systems and specifically highlights CAM-compatible tooling data. Why is that digital data so critical?
Because of the cost of failure. We talked about those massive, complex battery housings. You cannot afford to run a test part and ruin a $1,000 block of aluminum just to see if the tool path works.
Right.
You need to simulate the entire machining process in a virtual environment first, a digital twin.
So the tooling company provides the digital twin of the cutter.
Exactly. They provide a precise digital model of the holder, the insert, the cutting geometry, everything. And engineers load this data into their CAM software, their computer-aided manufacturing software.
So they can do their process development before they ever touch a real machine.
They run the simulation to check for collisions. They optimize the tool path to shave off seconds. They verify the cutting forces. All of this happens offline. By the time they push start on the actual factory floor, they already know it works flawlessly.
Which brings us perfectly to the final and honestly most surprising dimension of this deep dive. Sustainability.
Yes.
We always talk about EVs being green, obviously, but the manufacturing process is incredibly energy intensive, and the source makes this compelling argument that high-performance cutting tools are actually a major sustainability lever.
It's the concept of getting green via the gray world of manufacturing. If you want a greener product, you need a greener factory.
And how does a drill bit make a factory greener?
It all comes down to efficiency metrics. First is energy consumption per component. If you use a high-feed cutter like that neo-feed we just talked about.
To machine a structural part much faster.
Right. If that tool lets you machine the part in 5 minutes instead of 8 minutes, you just save 3 minutes of that massive CNC machine running its spindle, its hydraulics, its coolant pumps.
And you multiply that energy savings across 500,000 cars a year.
It is gigawatt hours of electricity saved just by using the right tool geometry.
The source also points to tool longevity,
which is huge. Tungsten carbide, the raw material for these tools, is a finite resource. Mining it is energy intensive. If a specialized Heli-Alu cutter lasts 3 times longer because its polished face prevents aluminum from sticking, you are consuming way less raw material.
You're manufacturing fewer tools, shipping fewer tools, throwing away fewer tools. The text mentions regrindable carbide tools and recyclable materials playing a big part here.
But honestly, the biggest sustainability factor is scrap reduction.
Right.
Think about it. If you are machining a complex motor housing, and at the very last step, your cheap boring tool vibrates and ruins the bearing seat, you haven't just wasted a tool.
You've wasted the entire aluminum casting.
You've wasted the energy used to smelt that aluminum, the fuel to transport it, and all the machine time used up to that point. Precision tooling prevents that waste. The dossier really frames process reliability as the ultimate sustainability metric.
It really reframes the whole conversation for me. We are so used to looking at the lack of tailpipe emissions as the only metric for EV sustainability. But this deep dive makes it clear that true sustainability actually begins with the efficiency of the industrial base.
You cannot have a truly sustainable product if it is built using a wasteful, inefficient process. If a factory has a high scrap rate because they are trying to save pennies on tooling, that EV rolls off the line carrying a hidden carbon footprint the consumer never even sees.
ISCAR's core argument is that investing in application-driven systems tools built for the specific physics of EV parts pays off massively in energy and material saved.
It absolutely does.
So, to synthesize everything we've covered today from the source material, the transition from internal combustion to EVs has forced a complete transition on the factory floor, moving from generalist machining to hyper-specialized integrated tooling systems.
It is completely polarized manufacturing. On one hand, you have soft, sticky, vibration-prone aluminum that demands polished, razor-sharp, high-speed cutters like the Heli-Alu family.
And on the other hand, you have silent, high-tolerance electric motors and hardened steel transmission parts that demand extreme rigidity and wear resistance from tools like logic turn and cut grip.
And tying that entire ecosystem together is the need for speed and modularity with systems like multi-master, combined with digital intelligence to verify everything before a single chip of metal is cut.
It is a totally new paradigm. It's not just about making chips anymore. It's about managing heat, managing microscopic vibration, and managing digital process data.
It really is.
You know, it forces you to look at a car completely differently.
Yeah.
Next time you see a new EV on the road, don't just think about the battery range or the software updates.
Think about the factory floor.
Exactly. Think about the polished rake face that kept the battery tray from warping. Think about the 3-flute drill that successfully cleared the chips out of the motor housing's cooling channels.
The performance and silence you experience on the highway is entirely dictated by the process stability inside the machine shop.
And that is a powerful, provocative thought to leave you with today. We often think of the green revolution in terms of big headlines, government policies, and solar panels. But based on our deep dive today, a huge portion of that revolution is actually happening microscopically.
It's all in the details.
It relies on the specific geometry of a carbide insert, working deep inside a factory you will probably never visit. How much of our green future is actually entirely dependent on the gray world of industrial tooling?
More than most people will ever know.
Well, thank you for helping us untangle the physics of EV manufacturing today.
It was a great discussion.
And thank you to everyone listening. Keep looking under the hood, or in this case, under the factory floor. We will catch you on the next deep dive.